In this lecture, we're going to discuss the electromagnetic spectrum. Now, the electromagnetic spectrum essentially describes all the different types of electromagnetic radiation. Now, before we examine the electromagnetic spectrum, let's define what electromagnetic radiation is. Electromagnetic radiation is essentially another word for electromagnetic waves. Now recall that all electromagnetic waves are composed of alternating electric and magnetic fields that are capable of propagating through empty space. In other words, unlike certain types of waves, for example, mechanical waves, which can only propagate through a medium, electromagnetic waves can propagate in the absence of a medium, in the absence of molecules, for example, inside a vacuum. Now, usually we symbolize electromagnetic waves in the following form. So let's suppose we have the x-axis, y-axis, and the z-axis, which is coming out of the board. Now, our electric field, which is given by the following green region, is moving along the y-axis. Our magnetic field, given by the blue region, is alternating along the z-axis. And notice the entire electromagnetic wave is moving in the positive direction along the x-axis. So, because the electric field lies along the y-axis, the magnetic field lies along the z-axis, and the wave is moving along the x-axis, that implies that the electric field is always perpendicular to the magnetic field, and these two fields are always perpendicular to the velocity vector, to the motion of our propagating wave. Now, to determine the direction of the velocity vector, we simply apply the right-hand rule. So we essentially take our right hand and we point our fingers in the direction of the electric field. Then we curl our fingers in the direction of the magnetic field. We extend our thumb and the thumb points in the direction of the velocity vector. Now, what about the magnitude of the velocity of any electromagnetic wave that is propagating through empty space? Now, the velocity of electromagnetic waves in empty space is given by lowercase c. And to calculate it, we can either calculate it in one of two ways. So we can either take the electric field and divide it by the magnetic field, or we take 1 and divide it by the square root of the permeability of free space multiplied by the permeativity of free space, where these two values are both constant. So we see that the value is 3.00 times 10 to the 8 meters per second. This is our velocity, the magnitude of our velocity, the speed of our electromagnetic wave that is moving in empty space. So, all electromagnetic waves travel with the same exact velocity in empty space. Now, let's begin our discussion on electromagnetic spectrum. So what exactly is an electromagnetic spectrum? So the electromagnetic spectrum essentially describes all the different types of electromagnetic radiation, all the different types of electromagnetic waves. Now, electromagnetic waves essentially differ from one another by the frequency and the wavelength. And the electromagnetic spectrum looks something like this, where this top line essentially symbolizes the wavelength given in meters of our electromagnetic wave, and this bottom line represents the frequency of our electromagnetic wave, and the units are given in hertz. So we see that we have radio waves, microwaves, infrared waves, we have ultraviolet waves, X-rays, and gamma rays. And notice this small section of the electromagnetic spectrum represents a very important type of electromagnetic radiation known as visible light or simply light. The reason that this is an important electromagnetic wave is because visible light is the type of electromagnetic radiation that is detected by the human eye. So if we essentially zoom in on this small section, we get the following diagram. So notice that on this side we have red, then we go to orange, then we go to yellow, then we go to green, blue, indigo, and violet. So we go from red all the way up to violet. So what exactly is the frequency and the wavelength range of visible light? So we essentially begin with red on the left side, and red has a frequency of about 4 times 10 to the 14 hertz and a wavelength of about 750 nanometers. Now if we go all the way up to violet, we see that violet has a frequency of about 7.5 times 10 to the 14 hertz and has a wavelength of about 400 nanometers. So one way to remember all these colors is to remember Roy G. Biv. So R stands for red, next we go to orange, next we go to yellow, which is somewhere about here, next we go to green, then we go to blue, then we go to indigo, which is somewhere here, and finally we end up at violet. So, notice that red electromagnetic radiation has a high wavelength and a low frequency, while our violet electromagnetic radiation has a low wavelength and a high frequency. So, let's examine the following example in which we're going to use the frequency to calculate what the wavelength of our electromagnetic radiation is. So calculate the wavelength of an electromagnetic wave with the frequency of about 7.2 times 10 to the 14 hertz. What type of wave is this electromagnetic wave? So to calculate our wavelength, we essentially use the following equation. So we know from a past lecture that the speed of light given by c is equal to the product of the frequency and the wavelength. So we know what c is. It's this value because we're assuming our wave is propagating through empty space. So we rearrange our equation and solve for the wavelength. The wavelength is equal to our c divided by the frequency. So 3 times 10 to the 8 meters per second divided by 7.2 times 10 to the 14 hertz, and that gives us about 417 nanometers. So that means this lies within the visible light spectrum, within the following region. And this color is about the color of violet, because violet has a wavelength of about 400 nanometers, and this is pretty close to that value. So, once again, the electromagnetic spectrum essentially describes all the different types of electromagnetic waves that exist. Now, electromagnetic waves all travel with the same exact constant velocity in empty space given by this value. And they differ from one another by the frequency and the wavelength of our waves. So we see that, for example, radio waves have a very low frequency and a very high wavelength, while our gamma rays have a very high frequency and a very low wavelength.